Assalamualaikum and hi everyone. Today we are going to continue our lesson for the subtopic 13.2, the kinetic theory of gases. The outcomes that at the end of this chapter, students should be able to state the assumption of kinetic theory of gases, solve problems related to the equation of ideal gas and pressure, discuss root mean square or RMS speed of gas molecules, solve problems related to root mean square or RMS speed of gas molecules. The kinetic theory of gases. The macroscopic behavior of an ideal gas can be described by using the equation of state, but for the microscopic behavior only can be seen by using the kinetic theory of gases. So in order to analyze the kinetic theory of gases, we need to make some assumption of kinetic theory of gases, which is the first one: all gases are made up of identical atoms or molecules, the same for all atoms and molecules. Then all atoms or molecules move randomly and haphazardly. So it moves randomly. The volume of the atoms or molecules is negligible when compared with the volume occupied by the gases. Then the intermolecular forces are negligible also except during the collisions. Interatomic or molecular collisions are elastic. The duration of collisions is negligible compared with the time span of traveling between collisions. Atoms and molecules move with constant speed between collisions, and gravity has no effects on molecular motion. Okay. For this subtopic, we will look at the three subcontents, which is the first one: force that exerted by an ideal gas, pressure on an ideal gas, and the third one is root mean square velocity of RMS. Okay, the first one, force that exerted by an ideal gas. By considering that an ideal gas of n molecules are contained in a cubical container of side n, as shown in figure here. Okay, so the atom here or the molecules here can move, okay, along the x direction or y direction or z direction. Okay, this molecule has mass m and velocity v. The velocity of v of each molecule can be resolved into their components, okay, such as the velocity along x direction vx, velocity along y direction vy, and velocity along z direction is vz. Okay, considering initially a single molecule moving with a velocity vx towards a wall A, and after colliding elastically, it moves in the opposite direction with a velocity of minus Vx. So this is the initial, the atom will move to the block, to the wall A, and then it collide with the wall A, and by elastically process, it will move again to the opposite direction of minus Vx. Therefore, the changes in the linear momentum of the molecules is given by equation of the delta Px equals to minus mvx minus bracket mvx. That means the changes of the linear momentum equals to 2 times of m times vx. Right? So the minus here, consider that this is the opposite direction. That means the molecules or atom has to travel a distance of 2d from A to B and back again before it collides with another wall, with wall A. The time taken for this movement is given by equation delta T equals to 2 times d over Vx. Vx is the velocity along the x direction. if we take the Fx1 is the magnitude of the average force that exerted by a molecule on the wall in this time of delta t, then we get the equation here. The average force that exerted by the molecules, number 1 equals to delta px over delta t. So delta px equals to the magnitude is 2 times m times vx over delta t is 2 d over vx. Then we know that from here you can have the equation F for the x direction for molecule 1 equals to m times d times the velocity of molecules along x direction squared. When we have the n molecules of the other gas in the container, that means we must plus up all of the atoms in the container until from number 1, atom number 1 until atom number n. Okay, and then we will get the general equation for the force, average force exerted by molecules in the container is m over d bracket the velocity squared of x plus velocity square of x2 and velocity square of until n. Then we will get the mean or average value of the square of the velocity in the x direction for the n molecules is here. It's the notation how to write down the mean square of velocity. Okay, the mean square of velocity, we must put this kind of the notation. Okay, equals to vx1 square plus vx2 square plus vx3 square until vxn square over n. And then by rearranging this formula, we will get the formula here. The force that exerted, or the average force that exerted by the all molecules in the container equals to m over d times n. N is the number of molecules in the container times the mean square of the velocity. The mean square of velocity vx squared. Okay, this is for x only. And then for average forces exerted at the y, so it will be Fy equals to m over d and the mean square velocity of Vy, and also for the Vz equals also. So that means the magnitude of the velocity V is given by equation V square equals to Vx square plus Vy square plus Vz square. Then we can have then we know that the total of mean square velocity of the velocity equals to Vx, the mean square velocity of the Vx plus mean square velocity of the Vy plus mean square velocity of the Vz. Okay, now we know that since the velocities of the molecules in the ideal gas are completely random, okay, so we can predict which side or which direction it goes. There is no preference to one direction or another, hence we will get the value for the mean square velocity for the x direction equals to mean square velocity for the y direction and equal with the mean square velocity of the z direction. So that means for the total up of the mean square velocity in the container equals to 3 times of the mean square velocity of the x direction. Okay, and then by rearranging the formula, we can get the mean square velocity of the x direction equals to the total of mean square velocity of the molecules in the container over 3. Then we get the final equation for the force that exerted by the molecules in the container is here F equals to N over 3, and it's a number of molecules in the container, times or bracket M times mean square velocity of the molecules in the container over D. So this is the equation, the last equation that we have for the force that exerted by the ideal gas in the container. Okay. The second one, the pressure of an ideal gas. We know that definition of pressure, P equals to F over A. F is the average force over area. The area is equals to, okay, from this condition, A equals to D squared. D times D equals to D squared. And we know that the force that exerted by the molecules in the container is equals to N over 3 bracket M times mean square velocity for the molecules in the container over D. Okay, and then by rearranging the formula, okay, you can have this kind of equation where the P equals to 1 over 3 bracket N, the number of molecules in the container, times M is the mass of the molecules over volume, times the mean square velocity of the molecules in the container. So here we get the equation for the pressure of an ideal gas in the container. And then for the rearranging formula, we can have the PV equals to 1 over 3 bracket NM times the mean square velocity of the molecules in the container. Okay, so the second one, and then we have, since the density of the gas rho is rho, okay, RHO, rho is given by the equation rho equals to N times N over V. N times N is the number of molecules in the container. Okay, so we can have the equation. Now the P, the pressure, equals to 1 over 3 rho times mean squared of velocity for molecules in the container. Okay, so this is the equation that we have for the pressure in container by the gas. Rho then P is pressure by the gas, rho density of the gas, and here is the mean square velocity of the gas molecules in the container. Okay. The third one, we will look at the root mean square velocity of VRMS. Is defined as VRMS equals to square root of mean square velocity. And then here we can get the equation by using the Boltzmann constant, PV equals to NKT. Then equate these two equations, we'll get the NKT equals to 1 over 3 NM times mean square velocity of the molecules in the container. And then we get here, okay, the mean square velocity of the container, of the molecules in the container, equals to 3 KT over M. Okay, now we square up this one, we'll get therefore the VRMS, the root mean square velocity, okay, equals to square root of 3 KT over M, or VRMS equals to square root of 3 RT over M. Okay, where K is the Boltzmann constant, T is the temperature, M is the mass, alright. Then R is molar gas constant, T is the temperature, M is molar mass. Okay, molar mass. Okay, then so the abbreviated VRMS equals to root mean square velocity, M mass of molecular gas, M, the capital M, is a molar mass of a gas, T is absolute temperature. Okay, now since we have the rho equal P equals to 1 over 3 rho times mean squared velocity. So by rearranging this formula, we will have the mean squared velocity equals to 3P over rho. Okay, and then when we square root this one, we will get the final equation for the relationship between the VRMS between P and Q is VRMS equals to square root of 3P over Q. So that means we have three types of equation for the VRMS concerning with the mole of gases, concerning with the number of molecules in the container for the gas. Okay. Now we look at the example 13.3. 8 gas molecules chosen at random are found to have speeds of 1, 1, 2, 2, 2, 3, 4 and 5 meter per second. Determine the mean speed of the molecules. Mean speed of the molecules. B. The mean square speed of the molecules. And C. Root mean square speed of the molecules. Okay, in order to solve this question, we need to grab up all of the information that given in the question. Okay, such as what? The number of molecules is 8, right? And then also the velocity of each of the molecules here from 1 to 5. Okay, the mean speed of the molecules is given by equation the sum of speed from number 1 until number n over n. Okay, so you must put the number here 1 meter per second, 1 meter per second plus 2 meter per second until 5 meter per second over 8 number of molecules. So we get the mean speed of the molecules is 2.5 meter per second. Okay, this is the answer for the mean speed of the molecules. B. The mean square speed of the molecules is given by equation here. The mean square speed of the molecules equals to the summation of V squared from number 1 until number n over n. Okay, so we put the number in the equation here. 1 k squared plus 1 squared plus 2 squared until the last one 5 squared over 8. 8 is the number of molecules. Okay, then we get the answer here. The mean square speed of the molecules equals to 8 meter squared per second squared. Okay, class. Now C. The root mean square speed of the molecules is given by equation VRMS equals to square root of mean square speed of molecules. Just put the number in the equation. We will get the VRMS equals to 2.83 meter per second. Okay, now you get the answer here. Okay, for each of the question asked. Okay, now we go to the example 13.4. A cylinder of volume 0.08 meter cube contains oxygen gas at a temperature of 280 Kelvin and pressure of 90 kilopascal. Determine the mass of oxygen in the cylinder. B. Determine the number of oxygen molecules in the cylinder. C. Determine the root mean square speed of the oxygen in the cylinder. Given that the molar gas constant is 8.31 joule per mole per Kelvin, K is the Boltzmann constant equals to 1.38 times 10 to the power of minus 23 joule per Kelvin. Molar mass of oxygen, the capital letter of M equals to 32 gram per mole. Avogadro number Na equals to 6.02 times 10 to the power of 23 per mole. Okay, this is the standard given in the question. And then in the question also we can have some kind of information that given, which is the volume V equals to 0.08 meter cube, the temperature equals to 280 Kelvin, and then the pressure P equals to 90 times 10 to the power of 3 Pascal, or P equals to 90 kilo Pascal. So now, in order to get the or to solve the question A, we must use the equation of state. The PV equals to N times R times T. So N is the number of mole. Okay, and number of mole. Now, and we know that the N here, number of mole here, is M mass for the gas over molar mass. M, capital M, is molar mass. Just put M over N in the equation because we need to determine the mass of the oxygen, the mass. So that means we must find out the equation that relate with the mass. Okay, now we put the N equals to M of gas over M molar mass in the equation. Okay, and then you just substitute the number in the equation, which is here is the P 90 times 10 to the power of 3, V is 0.08, and then M gas over, here is the molar mass for the oxygen gas, here is 0.032 because we must use the standard unit. Okay, standard unit for the M is kilogram, right? But it's given in gram per mole. That's why we need to change to the kilogram per mole. And then here is the R, the molar gas constant 8.31, and here is the temperature 280. Now we get the value for the mass of oxygen here is 9.90 times 10 to the power of minus 2 kilogram. Okay, this is the answer for the question A. Now for the B, the number of oxygen molecules in the cylinder. Okay, we need to determine the number of oxygen. Number of oxygen abbreviated by N. Right. So, from the equation of number of mole here, N equals to M gas over Mn. N is also equals to capital N over Avogadro number Na. So, we will rearrange the formula. We get the number of oxygen N here equals to M, the mass of gas, over molar mass, capital of M, times Avogadro number. Just substitute the number in the equation. Okay, N equals to, mass is 9.90 times 10 to the power of minus 2 kilogram over the molar mass for the oxygen is 0.032 times the Avogadro number 6.02 times 10 to the power of 23. So we get the number of oxygen molecules in the container or in the cylinder is 1.86 times 10 to the power of 24 molecules. Okay, this is the answer for question B. Now the last one, answer for the question C, we need to determine the root mean square or speed of oxygen molecules. So we use the equation of V RMS lah. Okay, V RMS equals to square root of 3 RT over M. Just substitute the number in the equation only, then we can have the answer here is 467 meter per second. Okay, right. So now we have gone through to the two examples. Okay, hoping that students can use this example as your references to do some exercise after this. Okay, that's all class. Thank you very much.